Well, good morning, everyone. Welcome back. We have had 2 sessions already, talking about the basic concepts of exploration seismology and the acquisition systems, including pre-processing. From today, we will start with some serious business, talking about seismic data processing and the imaging. So lecture 3, there's a concept called deconvolution and the filter. Actually, this is one concept, but in a different domain. So this session will include 6 parts. We will review what we learned in the day 1 about the Z transform and the implementation of a convolution and the correlation in the Z transform domain. Then we talk about the filters, inverse filters, and the phase. So we're distinguishing different filters by their phase. The third part, we will discuss issues related to the filter application. And then the second half of the session, we're talking about something called the least squares inverse filtering. And follow that, we have 2 examples. One's called sparking deconvolution, one's called particular deconvolution. If some of you have learned about the inverse problem theory, so least squares is one of a very fundamental inverse problem theory. Part 1, convolution and correlation in the Z transform domain. Recall that in the day 1, we introduced the Z transform. So for a time series, in this case, from negative infinity to positive infinity, I just need to emphasize, we call this series conventionally time series, right? But the axis here is not necessarily be time, could be space, right? We just because we are going to do Z transform, we just simply called time series, right? That time, not necessarily be time, can be space. So maybe the receiver location along the surface, that's also a time series, okay? For this time series, it's Z transform is expressed in terms of a polynomial, and each term has a coefficient corresponding to the magnitude of samples, and the power of Z is the index of a time sample. Right, that's the Z transform. And we also introduced Z is an operator for unit time delay. Right? So if we separate, if we try to distinguish different samples at different locations, basically check the power of Z. When we introduce that transform, we realize the coefficients of that transform are the sample value of a time series. That's what we just said. And the important thing is, if we use this operator, which is a unit delay operator, unit time delay operator, we use this operator to replace the Z in the polynomial, we end up so-called discrete Fourier transform, DFT. I think most of you think about DFT is derived from discretization of a continuous Fourier integration, right? But in fact, it's not. It's from here. It's from discrete Fourier transform. We will see later. I will mention that one of the important properties for the DFT is you assume time series is periodic. It's not like this case from negative infinity to positive infinity. But in fact, you have a limit time duration, limited number of samples. And in the DFT, you assume the original time series is periodic. So every, for example, if you have n samples, every n sample you repeat so many times. Okay. One of the advantages in the when we introduce that transform is for the convolution. In the Z transform domain, convolution becomes fairly easy. Simply, you multiply two Z transforms. Because the Z operator is complex one, it's complex operator. So this leads to the Fourier transform, right? Equivalent to Fourier transform. So in the Fourier transform domain, the multiplication means you multiply two amplitude spectra, and the phase, you simply sum them together, right? Because Fourier transform, in the Fourier transform domain, each sample is a complex value. You have a magnitude or amplitude, right? But also have phase. So the multiplication of two complex values becomes a multiplication of amplitude spectra and addition of a phase. We also learned the correlation. Correlation basically almost identical to the convolution, but one of the time series is in the reverse time order. That's different, right? And the multiplication of two complex number here for the correlation will be slightly different from a convolution. For the correlation in the Z transform domain or Fourier transform domain, it is a multiplication of one Z transform with a conjugate of another Z transform, right? So that means conjugate means you change the symbol in the front of imaginary symbol, right? Change the sign of in front of imaginary symbol. So that means you amplitude part, you just multiply two amplitude spectra, but the phase, you will implement subtraction here. So let me repeat this, try to make it clear, right? Let's talk about implementation, either convolution or correlation in time domain and the frequency domain separately, okay? Let's focus on time domain. Time domain, we know how to do convolution. In the time domain, we keep one time series in the ordinary order, but another time series, we make the second time series in the reverse time order. And then you do the superposition, which means the correlation. But the correlation itself in the time domain just simply do the two time series in the original time sequence, do the correlation, right? So this is in the time domain difference between the correlation and the convolution, right? Basically, convolution, for the convolution, you need time reverse order another time series. That's the difference. In the frequency domain, the convolution is simply a multiplication of two complex values, right? And for the correlation, in the complex domain, in the Z transform domain or Fourier transform domain, is the Z transform of one time series multiplied by the conjugate of a second Z transform. So this is different. Right. After we reviewed convolution and correlation in the time domain and frequency domain or Z transform domain, we can now discuss the filters, the core part of this session. Filters and the inverse filters, basically they are, in terms of implementation, they are identical. But right, when we're talking about filter, means we in the in this case for the convenience, we just simply concede the filter is a weighting coefficient applied in the frequency domain, right? You have a time sequence after Fourier transform. That's the, if we say you have a seismic trace, after Fourier transform or Z transform, you generate the Fourier transformed spectrum, right? Or spectra. And the filter, you simply acting as a series of weighting coefficients, right? And then you multiply the weighting coefficient to the individual frequency, right? So in terms of implementation, filters and the inverse filters are identical, right? But the difference between different filters we'll see from the phase. That's what we try to say. Give you a simplest example of a filter, which is a dipole filter, which dipole means you have two samples, right? Dipole in the electricity field or magnetic field, dipole means you have two elements, right? Positive, negative, right? So in this case, I give you a simplest filter which has only two samples, x0 and x1. x0, x1 could be positive, could be negative, right? Okay, even 0 is fine, but it's just two samples. Based on the two samples, based on the magnitude of the two samples, or power of the two samples. So power means square of each sample, right? Or energy. If the front one, x0, magnitude of x0 is larger than the magnitude of x1, this filter we call the minimum phased filter. If the magnitude of x0 is smaller than the magnitude of x1, this filter is called the maximum phased filter, right? So based on the two samples, we have two types phase, two types filters. One's minimum phase, one's maximum phase, right? So these two filters have a same amplitude spectra, but different phase spectra. Why is the same? Well, why they have a same amplitude spectra? Because if we recall, when you learn the Fourier series, there's something called energy conservation, right? In the time domain, energy is squared of each individual amplitude. So x0 squared, x1 squared, right? In the frequency domain, energy will be same as the time domain. So in the frequency domain, your energy will be squared of all the amplitudes, right? So because in the time domain, the energy is fixed, x naught, x1. So in the frequency domain, even you have a phase difference, but the energy will be the same, right? So you can understand in this way. Let's talk about the minimum phase dipole field. In the signal processing field, we call this minimum phase filter as front-loaded, which means this filter has the most energy at the front of a filter or wavelet in seismic context, right? So this most energy is in the front. If we go back to the previous here, so basically this one's energy means squared, so x naught squared larger than x1, right? This is called the energy front-loaded. Why this minimum phase filter is important? Because this one has a stable causal inverse. Well, let's talk about this. Inverse means your original filter is A plus BZ or X naught plus X1Z, right? Inverse that's 1 over that. 1 over the field, that's the inverse field, right? If we take a factor A to the front, we end up in the bracket here. In the bracket here, we have a 1 over 1 plus this factor multiplied by Z. Right, magnitude of Z, remember, is a pure phase operator. So magnitude of Z is 1 because it's EI omega t, right? Or EI omega delta t. So this is 1. So the magnitude of this totally together actually depends on the magnitude of B over A, right? If we record when you learn the Taylor expansion, one of the conditions, if we can record it, 1 over 1 plus x, if you can apply a Taylor expansion to this fraction, the condition is this x must be smaller than 1, right? Just talking about a positive x. You also learn of 1 minus x. Again, x should be smaller than 1. So in general, for both cases, positive and negative, basically the absolute value or magnitude of B over A should be smaller than 1. Otherwise, you cannot do the Taylor expansion. But okay, you say, what happened if I do make a Taylor expansion? What happened? That means if this condition is not satisfied, this Taylor expansion will not converge, right? So the condition is if absolute value A greater than B, if means the factor of B over A has a magnitude less than 1, this Taylor expansion will be converged, right? Okay, converge, they have 2 meanings here. One, it's a stable, numerically it will be stable, right? It's stable calculation. So that means if you truncate the time, the Taylor expansion by, for example, order n, right? And if you compare to the next one, order n plus 1, if we include one more term, your accuracy, this basically Taylor expansion is an approximation, right? The accuracy between the Taylor expansion and the original analytical function will be much higher. So including more terms in the Taylor expansion, accuracy will be much higher, right? So you stably eventually towards 0, the difference between these two terms, between these two expressions. That's stable. And because, as we said, if we have a more term, that means including more energy. But the amount of energy you include will be smaller for the order higher, right? So that means your energy is in the front. That's a causal. Causal really means if we have the time series have no negative time energy. The causal really means when you trigger the seismic signal, everything will record after time 0, right? You do not have any elements in the negative time. That's the causal really means, okay? We will see next example to see what's the acausal. Let's see the example we discussed in the first session. Surface ghost, either in the source side or receiver side. You have either source or receiver, air gun or hydrophone at this point, right? You have a wave propagating down, but you also another one go to surface, come back. Well, that's actually the 1D model, right? But just for the visualization, we draw this like a 2D, okay? But here we only consider 1D. So this one, the yellow one here, has a time delay of 2D divided by V. That's the time delay. And then in terms of index of time sample, we divide by delta t, which is time sample, right? Because in the Z transform, the power of Z is the index, not time. So that's time is 2D divided by V, and this time divided by delta t becomes index. Remember that? So the Z transform, in Z transform, the power is index. Okay, this is a typical example of a dipole, which has 2 elements. First one is 1, second one is R, which in this case is the reflectivity at the surface. Very close to -1, right? That's in the marine environment. That was a minor phased filter. No talking about the maximum phased filter. For the dipoles, we have 2 elements. The second one is larger than the first one. That is a maximum phase. That's the maximum phased filter. In the signal processing community, we call it backloaded, so energy at the end. Most of the energy is at the end of the filter. In this case, the wavelet. For maximum phased filter, it does not have a stable causal inverse, just opposite to the minimum phase filter. Right? For this inverse filter, 1 over A plus BZ, if we conduct the Taylor expansion, this Taylor expansion will not converge because the A here is smaller than B, absolute value, all right? Or B over A, this factor here is greater than 1. You can see if it is greater than 1, for example, if B over A is 2, what happens for the power? If power 3, power 4, so when you increase the value of power, this factor becomes larger, right? So it's not converge. You expect the truncated part should have smaller energy, but in this case, actually truncated one, because truncated parts have a higher order, the energy becomes large. So if we truncation actually cause more errors in terms of approximation. So this is does not converge this filter, right? In terms of causal or acausal, this inverse inverse has to be acausal, which means if we want a properly represent 1 over a plus b, that you not only have a positive part from arrow from 0 to infinity, but you also need a negative part from arrow 0 to negative infinity. So you must have coefficients before t equal to 0. That's the acausal, right? We discussed the simplest filter, which only has 2 samples, which called dipole filter. In general, the filter may have more than 2 samples, right? Could be 200, could be 300. So any Z transform polynomial can be factorized into product of the 2-point polynomial. We learned this in high school, factorization. For example, for this general filter has n samples from 0 to n minus 1. The Z transform is a polynomial of x arrow, z arrow polynomial. And this one can be factorized. So this large pi here, this is a symbol for multiplication, right? So this becomes x0 multiplied by 1 minus a arrow z. This is one factor, but the arrow from 1 to n minus 1. So you can have n factors. The first factor is x0 here. And then you have n minus 1 factors in total, n factors. And this n factors multiply each other, right? If you remember, in the first session, we talked about 2 Z transforms, multiplication of a 2 Z transform is equal to the convolution, right? So that means here, 1 Z transform multiplied by another Z transform, this is one of the convolution. And multiplied by another Z transform, this is another convolution. Another factor multiplication here in the time domain is another convolution. So really means this filter can be expressed in the time domain as a product in the Z transform is a product, but in time domain as a convolution of dipoles. Right? So you decompose your filter into so many dipole filters, and you just do 1 by 1 a convolution of dipoles or product dipoles. That's the general case. Now how to deal with the difficulty we found in the maximum phase field. We need this concept called equivalent filters. If there are 2 dipoles, one's A, B, one's B, A, their energy, x squared plus b squared equal to b squared plus a squared, right? The energies are the same. So we call this filter, or we call this dipoles, like equivalent filters. Equivalent means not identical. What's the difference between the 2? Basically, A in the front, this one A at the end. The difference is a phase, right? So this is if A, B is a minor phased, B, A will be maximum phased. So equivalent filter dipoles can be distinguished by the phase properties, either minimum or maximum phase. That's the concept. We will use this concept to smooth out the difficulty for our inverse filter. Talking about phase properties, we already mentioned that. For general filter, which can be factorized into a series of factors, right? Multiplication of many dipoles. When all dipole factors are minimum phase, this filter is called a minimum phased filter, right? When all dipole factors are maximum phase, that filter is called the maximum filter. Of course, sometimes you have a minimum dipoles, maximum dipoles mixtured. So the mixed phase filter basically is when the dipole factors are mixture of a minimum and the maximum phase, right? We're really interested in the minimum phase filter, in fact. So let's compare the minimum phase and the maximum phase filters. Minimum phase filter, we just said in the previous slides, dipole factors all are minimum phase. That is the minimum phased filter. In this minimum phased filter, energy is the most front-loaded of all filters with the same amplitude spectrum. So if we give you the opportunity, if we construct any types filters, any filters, but those filters will have the same amplitude spectrum as the one we have here, you're guaranteed this minimum phase filter is the most front-loaded filter compared to any other filters, right? Just mathematically give you a definition, okay? One of the important properties, as I said, we are in favor of a minimum phase filter. It's because its inverse is also minimum phase. That's important, right? For maximum phase field, the dipole factors or maximum phase. Make sure all maximum phase. Otherwise, the mixed phase. So energy is the most backloaded if you compare to any other filters. They have the same amplitude spectrum. That's the maximum phase. Minimum phase, maximum phase, because you have so many samples in the filter, you are not guaranteed always have minimum phase or maximum phase. So there's something called a mixed phase. Dipole factors are mixture of a minimum and the maximum phase. That's the mixed phase field. The inverse, if we implement inverse of the filter, the inverse will have both a causal and a causal components, right? For the causal component, which come from minimum phased dipoles, but also from maximum dipoles, right? Inverse is also mixed phased. So that means it's not guaranteed to be converged because the maximum dipoles involved. Right. One special case is zero phase. Zero phase is not minimum phase, not maximum phase. What is zero phase? Zero phase means your phase components is all the components of a phase are 0, right? Phase is 0 for all frequency components. Transport filter into the time domain, you will see this filter or wavelet is symmetrical in time. Symmetrical in time means you have a peak at the middle, you have a gradual decayed amplitude in the positive time, but you also have energy in the front. So this is a causal. You have an energy before your time 0, right? This one, because a causal, which means you have something recorded before your source is triggered. It's not physical. So this filter is non-physical, right? However, this filter is also important because it has the highest resolution of any wavelet if they have a same amplitude spectrum. If we compare minimum, maximum phased, right? This 0-phased wavelet has the maximum resolution. We will see example later. This inverse, because the maximum phased, the mixed phased, this inverse has both causal and the causal component. That's the same as the maximum phase, mixed phase filters, right? 0-phase filter is a mixed phase filter. In this picture here, that one, when we said energy front-loaded, so strong energy in the front, that's called a minimum phase. And if the strong energy backloaded at the end of a wavelet or end of a field, this is called maximum phase, right? In between this mixed phase, if you do a factorization of that transform, you end up not only minimum phase dipoles, but also maximum phase dipoles. So this is a mixed one. That's the illustration of a minimum phase, maximum phase. We said the 0-phase is a special example of a mixed phase filter. I showed this diagram in the previous session. This talking about when I showed this diagram, we're talking about the bandwidth. The bandwidth has a significant effect to the resolution of wavelet, right? In this case, 0 to 150, you have a very narrow spark. When the band gradually smaller, you can see the spark gradually wide, fatter, and finally, practically maybe have 8 Hertz to 30 Hertz, much wider. Nevertheless, these 4 wavelets are 0-phased because time 0 here, positive, negative time, they are symmetrical, right? Because they are 0-phased, that we do not only have positive time energy, but also have energy before time 0. So they are a causal, right? But this one is a very high resolution, means this, although this wide in the time domain, but this peak here very well represents the seismic reflectivity, or geologically very well represented the position of an interface. You can see that. So this is much easy for geological interpretation. That's why we call it minimum phase, a zero phase filter or zero phase wavelet as the highest resolution. So one of our objectives in seismic data processing is to somehow to compensate your data or process your data to make the final seismogram, final seismic trace as zero phase. In the first session, we're talking about the factors which influence your seismic data. One of the important factors is attenuation, right? So different frequency components have a different rate of attenuation. And in your seismic data, because high frequency have a strong attenuation in your seismic data, most likely the wavelet is minimum phased, so energy front-loaded, right? But one of the processing steps is to try to compensate the high frequency attenuation. So after compensation, you can make your original zero phase wavelet reappear in your data, right? One of the seismic sources we learned is vibe seismic, if we remember. The vibe seismic actually is the correlation between the sweep and the record signal, right? So the ideal wavelet is zero phase wavelet for the typical vibe size signal, right? But because of attenuation, your wavelet appeared in your seismic trace could be minimum phased. So after the compensation, after the attenuation compensation, you end up zero phase. Zero phase is the high resolution wavelets. For the dynamic seismic, if we use dynamic source instead of a web size, very likely you have we call the minimum phased wavelet, right? So energy in the front and the energy decays. It's not necessarily geometric decay, but at least you can see energy is front loaded, right? That's for different frequency range, frequency bandwidth. For the 0 to 250 hertz, you have a spark here, and this 8 to 9 hertz is a filtered spark. Effectively means you have this one from 0 to 250 hertz, full band, and this one you simply apply a bandwidth filter to the spectrum of this one, and the bandwidth between 8 and 90 hertz, you end up wavelet look like this, right? And between 8 to 70, the filter after the filtering time domain signal look like this, and the 8 to 30 look like this, right? They all are minimum phased in this case because of the energy front loaded. That's the two examples. Now we're talking about the applications. When we apply a filter, we can implement the filtering in two domains, either in time domain or in the frequency domain. In the time domain, we call it convolution, filtering convolution, right? And in the frequency domain, the filtering means the modification of original Z transform original seismic trace and the Z transform of the filter. So this is two implementation, right? Theoretically, we can do both. We can do either way, right? And theoretically, the choice depends on the convenience, efficiency, and the effectiveness. But in the seismic signal analysis, most likely 99% time, you implement them in the frequency domain, right? In the frequency domain implementation, actually, the filtering includes 3 steps. First step, you transfer your seismic trace to the frequency domain by Fourier transform. And in the frequency domain, you multiply the frequency spectrum of seismic trace by a filter, which means you multiply weighting coefficients to individual frequency components, right? And then after the filter, you transform the filtered spectrum back to the time, right? Okay. You will see, I said, most likely we implement the frequency domain, but it seems quite complicated because there are at least 3 steps, right? Forward Fourier transform, inverse Fourier transform, in between a modification. But because Fourier transform is very, very fast calculation, so we almost can, or we cannot completely ignore it, but definitely it's very, very fast, very efficient. So the efficiency is achieved by something called a fast Fourier transform, much faster than DFT. In the first session, I said, for DFT, how the DFT implement is when you have a time series, for example, if we have n samples, after Fourier transform, you have n components in the frequency domain, right? That's the DFT. When you implement Fourier transform, the second half, which have n/2 half, second half can fold back to the front half. So you end up the total length of n/2, right? So you save 50% time. Not exactly 50, because for Yanghua, you have a addition here, right? That's quite minor. Right, now, original time series n samples, after the one folding becomes half, so it's n/2. For the new time series, which has a length of n/2, you folding again, you end up n/4, right? And then you so on and so forth, you end up 8 samples, fold again 4 samples, fold again 2 samples. Of course, 2 samples cannot afford, right? So at the end, you only need to calculate 2 samples Fourier transform, okay? Why we can do that? Because in the Fourier transform domain, in the Fourier transform, the Fourier kernel is sine, cosine functions. So they're periodical by 2 pi circle, right? So one of the issues for the FFT is you need the length of a time series to be a power of 2. If the length becomes exactly power of 2, as I said, original calculation, you need n square calculations, but now you only need n multiplied by log base 2. log n. So it's a very much simpler calculation. Well, much faster. If your real data time series is not exactly power of n, what you need to do, you need to add in zeros at the end of a series. That's called zero padding. Right. That's very important. You should be just used to that. Every time when you write a code involves Fourier transform, you should always pad in zero at the end, right? Make sure that after padding, the time series is power of 2. Adding zeros to your original time series does not change the Fourier transform, right? Because adding zero there only for your folding, but it does not change the original Fourier transform. Because as I said before, it's energy conservation. It's still the same energy. If you didn't do enough zero padding, what happens? As I said, Fourier transform is a function of sine, cosines, right? They are periodical in the frequency domain. And in the first session, we said Fourier transform basically is sum of sine functions, cosine functions, right? For each individual frequency components, the sine function is from negative infinity to positive infinity. So you assume your data in the time domain is periodical. The time at seismic trace is periodically repeat many times, right? That's one of the assumptions made by Fourier transform. Okay, so for example, for this frequency domain, they assume in the time domain, you have one of this, one of this, one of this, repeated many times, right? They're all identical, but different time. So you end up this result here. Okay, because you do not have sufficient zero padding, the end of this time series will overlap with the front of the next time series. End of this time series will overlap with the front part of the next time series. Or wrap around. Okay, so if you have sufficient padding, you can see maybe you have an original signal here, you have a gap here, which is zero padded, right? And not same time series and another gap. This gap means zero padded, right? So you separate them. So after the inverse Fourier transform in the time domain, you can easily cut off anything just at the point of padding, right? Otherwise, they're overlapped. So this overlap. This is called wraparound. Okay. If we, I will show you some examples of wraparound. I actually showed it before when we see seismogram from websites. We do see some energy appeared before the first arrival. Those energy, I just said at that time, is maybe you use the AGC, you boost the background noise, right? But maybe you use a Fourier transform when do the correlation between the sweep and the recorded signal in the use of frequency transform method. You actually maybe have a wraparound in front. We'll see many examples later. Another issue in the Fourier transform domain filtering is Gibbs phenomena. That's a very important Gibbs formula. You will see in the seismic time domain seismic signal, you will see ringing, right? It's not smooth, but they have some ringing. Well, I'll show you examples, right? And fundamentally, another thing is the amplitude spectral filter is not smooth. Ringing means we're at the end of the field bands. But if we inside the filter, the amplitude also have a similar to ringing, but we should call it not smooth, right? So those two are the important principles we should apply to the field, right? And okay, so far I mentioned we do the convolution time domain, modification in the frequency domain. In fact, time domain and the frequency domain are relative, right? You can also do convolution in the frequency domain equivalent to the modification in time domain. That's relative, okay? So these principles apply to also time domain field. Same, basically, this principle for the filters. Okay, let's see what these two phenomena means. One is a Gibbs phenomena, one is the amplitude spectrum is not smooth. Right. The first number here, the first column is a wavelet. The first column are the wavelets. The second column, second row, sorry, the first row are the wavelets. Second row are the frequency domain filter. The first column here is boxcar function filter. Boxcar means you just have a squared boxcar here, right? You can see here, if we are bent between this frequency and this frequency, you shall keep it, which means you multiply this coefficient to your filter, and the outside should be 0. But here you can see it's not exactly 0. So that means you do not field completely. You have some leakage here of the filter. This the Gibbs phenomenon, right? This Gibbs phenomenon. The second important principle is the filter spectrum should be smooth. Okay, here on top, that's not smooth. You can have some frequencies after filtering, you're amplified because you multiply by a coefficient more than 1, right? 1 point something. Some frequency components are suppressed a little bit. You can see this system. So ideally, the top bit should be 1. So the most flat field. Okay? What causes these two phenomena? What's the facts caused these two phenomena? Actually, is this. The filter, edge of the filter, actually, you have two steep slopes. So this one, the slope is too steep, right? This one slightly wider, slightly lower than this. It's not a slope as this one. You can see front a bit. You have a slight slope here. You can see the phenomena of Gibbs phenomena, and also the top bit becomes much flatter. But ideally for this one, you need a gentle slope. If we have gentle slope, this ring is here, much smaller, and the top here is almost 1 flatted, right? In the time domain, you can see for the boxcar function, you have two phenomena, Gibbs phenomena, and the amplitude is not flat. You can see here, not only have a 0 phase filter in the middle, but you also have the ringing left to right. They're symmetrical, basically. They're 0 phase, right? If this one is better than the first one, but you have the filter has a steep slopes, you can see they still have some ringing on the left and the right. Ideally, you should have a time domain wavelet look like this, have a clear peak and a clear tube, and all the rest part have a very small amplitude. That's the important feature of a filter. Right. Another issue for the inverse filter is inverse filter basically is 1 over the filter, right? 1 over the filter. So another issue is if one of the components, AF, is 0 or next to 0, 1 over 0 is not exist, right? So the field is not stable. That's the problem. When AF is 0, so 1 over F does not exist, but maybe AF is not exactly 0, but next to 0. So 1 over F becomes a very huge number, right? So that's not stable. The one technique to overcome this problem is to add in something to the AF, which is WF here, it's white noise. Add into that, and the 1 over A plus WF, this one will be okay, even AF0, because this WF here is constant, it's non-zero. This processing called the pre-whitening, right? There's two concepts here, whitening. Whitening means we assume there are some noise in your data, and the noise is made of a series of random numbers, and the random numbers is in terms of spectrum is called a white spectrum, which means you have almost the same magnitude at all different frequencies. That's called a white spectrum, right? Just like light. The white means you have a equivalent magnitude for all frequencies, right? That's white. Pre-white means it's not really there. You just, before you do the inverse, you add in the white there, right? This concept, when we're talking about least square, this concept, in fact, is in terms of inverse problem, this concept actually is called model constraint. So you have data, but when you do the inverse calculation, you actually introduce something called a model constraint, right? And this parameter here, in fact, is a trade-off between the data fitting and the model constraint, okay? If you guys are interested in this, I have a book called Seismology, which is a textbook for the year 4, year 3 students. I taught it in the previous 10 or more than 10 years. So you can find more about this in the textbook. So how we do that? This is the amplitude spectrum of seismic data, frequency access, and amplitudes. You do the pre-whitening, basically you add in, we call the white noise, which means at all the frequencies, this noise have a same magnitude, right? You add that, that means you have any part, any frequency, is 0 value, right? So that means you can do the inverse of this one. But this one cannot, because here, 1 over 0 does not exist. That's the pre-whitening. Right. I think we finished the first half, and let's have a time break. I'll see you in 3 minutes time.